Hello again, everybody. Welcome back. This is Chapter 11, Rotational Dynamics and Static Equilibrium, and this is really the second part of our chapter right here that we're starting, the idea of static equilibrium. Now, we've actually done this topic before in our forces chapter. In static equilibrium, what that meant was that, or what that still means, is that all forces in any direction, whether it's the x direction or the y direction, are balanced out so that the object is not moving in the x or the y. That's still the case. But what is also true is that the net torque around any axis of the object is also zero. For example, let me illustrate something real quick here. So right here we have a rod, a bar, okay, and it is experiencing, we'll say, 5 newtons of force. Okay, so 5 newtons of force downwards there, and 5 newtons of force upwards right there. Okay, you could say that the net force in the y direction, let's just ignore the x for now, but the net force in the y direction is definitely going to be 0. There's a downward force. Maybe it's caused by, and we didn't even account for this, the center of gravity, the weight force of this rod. But there's also an upward force too, and you can see that these two forces, one up, one down, is canceling out. But it's not going to be in a static equilibrium because these forces are kind of offset from each other. All right, and if we call the center part the pivot point right there, or the axis of rotation, you can see how that would cause this object to kind of move around counterclockwise like that. What is true with static rotation, and what you can assume with static rotation, is net force in the x is 0, net force in the y is 0, but also the net torque about any axis is also going to be 0. If that's the case, then the object will not move. It won't move translationally, but it also won't move rotationally as well. Okay? A couple of things to think about when we set up problems like this. First of all, when dealing with the object's weight or mass, all right, treat the gravity as acting on the object's center of mass. All right? Like I showed you before, let me back up here a second. This black dot right here. All right, you could treat this rod as, even though it has mass all distributed along here, you could treat it as being all that mass times gravity being acting straight down in the middle like that. That would be your mg. Okay, so that's what we're being told on this slide right here. Nope, this slide right here. All right, treat the gravity as acting on the object's center of mass. Sometimes it may be difficult to find the center of mass, but in most of them, it's going to be a pretty ordinary object, like a rod or a sphere or something like that. Okay. Also, set the axis of rotation, all right, around which you're going to sum all the torques. Set the axis of rotation at the position of one of the forces. All right, and in fact, it's very helpful to pick the most complicated force, because what this does is this takes it out of the torque equation. Let me draw it again right here. Okay, so we have this rod right here, like that, all right, and we've got an upwards force, 5 newtons, and let's say we have, I don't know, 10 newtons downwards, all right, 10 newtons and another 5 newtons upwards like that, okay? We want to find, if you want to find the net torque, I can't draw a sigma right here, the net torque on this, all you have to do is pick some sort of rotation point. All right, the rotation point I'm going to pick is right here. All right, why did I pick that? Well, because this is a lot of forces going on right here. 10 down and 5 up. All right, so what that means is these forces are 0 radius away from that axis of rotation, which means they create no torque at all. So there's no torque created by these. These do create or try to contribute towards translational motion, but they don't contribute towards torque. So therefore, find some sort of a place where a force is acting, or the most complicated forces are acting, and call that your rotation point. Right? That means that, well, like right here, only this guy is creating any kind of torque around there because that's the only force that's being applied at some distance. Okay? So that'll help you kind of set these problems up. Okay, so we're going to do two problems right here. This example 11.5. Actually, it's the same problem, but we're going to do it two different ways, and we're going to illustrate that very point that I just pointed out to you, that you can put the axis of rotation, or you can assume the axis of rotation to be anywhere, because after all, if it's in equilibrium, it's not going to be rotating anyway, but you have to pick a point around which you could pretend that it might rotate. So in the first one, in part A, we're going to put the axis of rotation right here on the right end of this plank. And in part B, we're going to put it on the left end of the plank right here and see if the forces change at all. And the answer is that they shouldn't. Okay? So, we have force up by the woman, force 1 up by the woman and force 2 up by the man, and mg down by the kid that is sitting on here. All right. Now these values don't have any, these forces don't have any values, but we're going to state force 1 and force 2 in terms of mg. It's like, how much is this guy going to be lifting in order to support mg? How much is she going to be lifting to support mg, and so forth? So what we can do to solve for F1 is let's sum the torque around this axis of rotation. So the axis of rotation is on the right end right there, okay? And we're going to be making this our force. So let's write net torque. I keep making all these weird marks right here. Net torque. Again, if that end right there is the axis of rotation. Net torque. Well, we have two things acting on, two forces creating a torque around this axis of rotation right there. The child, is creating a torque in the counterclockwise direction, and this woman right here, lifting upwards, is creating a torque in the clockwise direction. Now we know counterclockwise is positive, so let's just go ahead and list that first. All right. So what kind of force is the child applying? The child is applying mg, and at what distance? Well, it's at L divided by 4. Okay, that's the distance, so that's the radius that the child, is applying his downward force from the axis of rotation. But in the opposite direction, in the negative direction that we call clockwise, the woman is applying her F1 force, so force upwards, force 1, at what distance from the axis of rotation? Well, it's that full length L, right? If this is L divided by 4, or 1/4 L, and this is 3/4 L right here, the whole length, it has to be L, which is why it's called L. All right? So, force 1 times L. All right? And that has to equal 0. Okay? That's the assumption, because if it's not rotating, it's going to be equal to 0. So let's solve for that F1 right there. If we know the net torque is equal to 0, then we can set all these equal to 0. So I'm going to add over this F1L to that side. So it's going to be mgL divided by 4 on the left equals force 1 times L on the right. And as you can see, the L's are going to cancel out. All right? So therefore, force 1 is going to be mg divided by 4, or 1/4 mg, which is basically 0.25 mg. So whatever the child's mass is in times gravity, she's only supporting 1/4 of that. Whereas we should be able to expect that the man is supporting a greater amount of that because there has to be 3/4 left to support. Well, let's just find out and make sure. Okay. So since all the forces in the y direction have to also add up to 0, now we can look at this by saying, all right, translationally, in a straight line in a y direction, net force in the y equals 0. All right, then we should be able to solve for the man's force, force 2. All right, he's applying force to upwards. All right, the child, mg, is going to be acting downwards. All right, and the woman, her force 1, is going to be acting upwards. All right, and that all has to equal 0 because we said it's static equilibrium. It's not moving in the x or the y or having any torque. All right. So let's get everything away from F2 right here. Force 2 equals mg plus force 1, right? And that's going to be mg plus, what is force 1? Well, we know what that is already. Plus 0.25 mg. Okay? Oh, and you know what? I realized that I messed up a sign. I messed up a couple things right here. Let's get rid of some of these signs. I put, let's go back to our summing of the forces right here. Force 2 is up. Mg is down. I meant to put, that's a plus sign right there, right? That force 1 should be a plus. And that's going to change a whole bunch of things. Well, not a whole bunch of things. Just one or two little things right here. All right, that's going to make that a minus sign, not a plus sign. I just realized that. And I still make mistakes. I catch them sooner than I used to. So when we add over the mg and subtract over the F1, that's going to be a minus sign right there, which is going to be that right there. Okay? So force 2 is going to be, what's mg minus 0.25 mg? That's going to be 0.75 mg right there, and that's our final answer for the force 2. So he's the man is supporting 3/4 of the child's weight than the woman is. Partly because the child is a lot closer to the man's end right there. All right, so keep those in mind. The force 1, 0.25 mg, and force 2, 0.75 mg, are what they are. And we're going to see if we can find get the same values if we do this in part B, where we put the axis of rotation somewhere else. All right. So here, the axis of rotation is near the woman. Is at the very end right there. So there's the axis of rotation there. Everything else is going to be the same. All right. So we're going to solve for, let's see, can we solve for the torque of this? No, we can't, because this force right here is basically out of the equation because it doesn't create any torque at all. But we can solve for this force first because it is applied at some distance away from the axis of rotation. It's going to be creating a torque like that, whereas a child is going to be creating a torque downwards, kind of like that. Okay, so let's make a statement about our net torque. Net torque right here around this axis of rotation on this end. That is going to be force 2 times, what's that full length of the board? It's just L, right? Force 2 times L. That's convenient. Let's see. That is in the positive direction, right? Counterclockwise is positive. So the minus direction is going to be what the child is applying it in, the clockwise direction. So the child is applying force of mg because of, looks like his weight. But what distance is that at? That is at 3/4 L right there. Okay? So, since the net torque around any point is going to be 0, we can then say, all right, well, force 2 times the length is going to be equal to, I'll get rid of these parentheses right here. I'll just say 3/4 mg L. Okay? Well, there's an L here, an L here. The L's cancel out. And so our force 2 is simply going to be 3/4 mg, which, as in our previous problem, was 0.75 mg. Okay? Still true. I think you can see where this is going. We're going to find that the force 1 is going to be the same as it was previously. But let's just go ahead and prove it. All right? And force 1, since we already know this upward force, and we know the downward force now, mg, of this child, we should be able to use translational equilibrium. Net force in the y direction, not torque anymore, but net force in the y. Net force in the y direction equals 0. And that equals the sum of all these upward and downward forces. So it's going to be force 1 up minus mg down plus, that's what I meant to do before in the previous problem, but messed it up, force 2 up. Okay, so for solving for force 1 is going to be, let's see, we're going to add over that mg and then subtract over the F2, right? Mg minus force 2. Well, it's going to be mg minus 0.75 mg. That's what we got from right up here, right? That is what force 2 is. Okay, and so force 1 is going to be 0.25 what am I doing here? mg. Just as true as it was before, all right? So you can put the center of rotation, the axis of rotation, anywhere you want, all right? But it makes the most sense. If you got a lot of forces kind of combined on one end right there, put the axis of rotation right there, because those forces are not going to be creating any torque, which means you don't need to deal with them, okay? So you can put the axis of rotation wherever you want, but some places are actually better than others. All right, thanks for hanging in with me here. This is going on 17 minutes. I think I'm going to wrap it up. If you have any questions, make sure you get in touch with me and ask me. But in the meantime, thanks for following along. I'll see you on the next one.